Hello everyone, Chicken Puck here. Today we are going to prove this statement here, which tells us the probability of measuring a particular pair UV after applying a quantum Fourier transform. It looks crazy, but simply what this is saying is the measurement doesn't give us arbitrary numbers. It gives us numbers containing information about a hidden discrete logarithm. So first things first, if you're not familiar with the Fourier transform, let's go over that. So for a quick example, let's say I play a musical note. What you hear is a sound wave traveling over time. So if I were to just show you the raw wave, it would be difficult to tell exactly which frequencies produce that sound. A Fourier transform takes that information and describes it in a different way. Instead of asking how does the signal change over time, it asks what frequencies are in that signal and how much of each of those frequencies are present. Think of it more technically as changing the basis in which we're describing information, i.e. signal to frequencies. Okay, so then how does this help us with quantum computing? Because these kind of periodic patterns that we see, which are really hard to understand as they come, become very obvious in the Fourier representation. Let's say I gave you like 1000, 1000, A repetition might be lost inside all these bits, right? So the Fourier analysis is designed to basically expose that information. So then the quantum Fourier transform simply uses that same mathematical idea, except now we're applying it to the amplitudes of a state. If you remember, we can write a quantum state as such. We can write a quantum state like this, and then these alpha x's are amplitudes. So then the QFT transforms these amplitudes into a new set of amplitudes. So largely speaking, what this is saying is we're changing from a computational basis idea representation to a different representation that makes periodic and group structure more easy to detect. So now let's get into the problem. Before we go into this problem, we have to cover another important topic, the discrete logarithm. Now, this is very important in cryptography. So classically, solving the problem h equals g to the d is simple. But suppose I gave you g and h and told you to recover d. For large groups, that reverse problem is computationally hard, and that asymmetry of going back and forth shows up in major cryptographic systems. So what we're going to do here, I'm going to explain to you how a quantum Fourier transform can get this number d. So rather than searching directly for d, what we can do is encode information about d into a quantum state, apply a quantum Fourier transform, and then prove that measurement gives us information about a modular relationship containing d. All right, let's get into the work. So first thing we're going to do is write this down here. Okay, now I'm going to assume you don't know what a projector is. So we'll go over what a projector is in quantum computing. So a projector is basically an operator that asks one question. Is the quantum state in a particular subspace? So if I have 0, if I have ket 0, so then the projector onto ket 0 is, okay? So then since this ket 0 equals 1, 0, and this is just the top left entry, if we apply P0 to ket 0, we get ket 0. If we apply it to ket 1, we get 0. Okay, let's get back into the problem. So given this projector, we have PUV, which is a projector onto the computational basis state, ket U tensor ket V. What this is saying is, did we measure UV? So next we have rho A. Rho A is the density operator describing the quantum state. So next we have this FG term with the rho A. So this term is the state after the Fourier transform. Okay, so then finally we have this full trace here. And this trace is the Born rule in density matrix form. So if you don't know what the Born rule is, I'll explain briefly. It's a rule in quantum mechanics which converts our quantum state into probabilities of outcomes that we can actually measure. So since we're using density matrices here, the Born rule takes its form from the trace of P rho. So now we're going to expand the trace. So the trace is just the sum of the diagonal elements. And our system has 2 registers, so we're going to use the computational basis. So we have ket R tensor ket S. Therefore, we have, so this is literally just the definition of the trace. So then now we're going to insert the projector here. And then we have, so next we have this form here. So as you can see here, the computational base states are now orthogonal. We can write the delta function here, right? And then these are 0 unless R equals U or S equals V. So then almost the entire sum disappears, leaving, so as you can see, we've reduced the entire trace to one element now. So now we're going to insert the Fourier transform state. So this is a long formula, but we have to write it out. Okay, this is, I know this is long, but we'll break it down, okay? Because of the orthogonality, this Vn here, and mv, because of the delta functions, the n equals the m equals the v. Almost everything disappears. So then looking at our complex exponential here, its relevant phase contains the n minus m, right? But n equals m, so then therefore n minus m equals 0. Therefore, e to the 0 equals 1. So then even this phase will disappear. So then what remains? This. Okay, we're gonna blow that up and explain it. Okay, so basically I wrote down the next step, but to understand it, I have to go over what a coset is. So a coset is basically a shifted copy of a subgroup. So if I have a group G, like here, and I have a group H, H is a smaller subgroup. So for an element G in G, a coset would look like GH. So what this is saying is all the shifted copies of H inside G. And this means how many cosets are there. Why is the coset important? Because we may have different shifts, right? But those shifts all contain the same underlying structure related to D. So then once the Fourier transform removes all that shift, every coset will contribute equally. So then all we have to do is just count how many cosets there are, which is here, right? So what's happening here, right? So the inner product does not depend on which coset we're summing over, so we can pull this outside. So now we're literally just adding 1 for each coset. So the sum equals the number of cosets. So since we have n here, we can just substitute. Just multiply this by n, right? Now, if you notice, that is what we were trying to prove, which is what we were looking for. This ending equation leads here. So now we can finally see what this trace was telling us. The quantum Fourier transform doesn't produce arbitrary measurement outcomes. The only pairs U and V that can appear with non-zero probability satisfy this. U equals dV mod n. So we started with a hidden discrete logarithm. D, we encoded its structure into a quantum state. We used the Fourier transform to then expose that structure, and that measurement gives us classical numbers containing information about D. And then under the modular conditions, we can solve that classically to recover the discrete logarithm. So what this is showing is that we can take hidden quantum structure, which becomes measurable classical information. Thank you for watching.